I'm Kaida Shiohara from the University of Tokyo. I'm glad to introduce our work, Detecting Deepfakes with Self-Rendered Images. Deepfake detection aims to classify facial images into pristine or forged. A face forgery detection benchmark, Face Forensics++, is widely used to evaluate model generality to unseen manipulations. As shown in the videos, deepfakes and face swap manipulate the target identity. On the other hand, face-to-face and neural textures manipulate the target expression. This is cross-manipulation evaluation results of state-of-the-art methods, including our approach. In the evaluation, the models are exposed to unseen manipulations. It seems all methods generalize well to unseen manipulations. So, has the problem been solved? The answer is no. Several deepfake detection benchmarks have been proposed so far. Examples of deepfakes are here. Especially on recent benchmarks, previous methods failed to generalize. We emphasize that the score represents the best result of all previous methods on each dataset. So, a method that achieves the best result on a dataset may be less accurate on other datasets. In contrast, our method achieves state-of-the-art results on all the datasets with a single model. Our solution is simple. First, naive image classifiers are not generalized to unseen fake samples because of overfitting to training fake samples. Our key idea to solve the problem is that training with more general and unrecognizable fake samples encourages the decision boundary to be more robust against the unseen domain. What are general defects in forged faces? As shown in the figure, we analyze common artifacts and classify them into 4 types. Self-rendered images aim to reproduce these artifacts. How do we get unrecognizable fake samples? Our observation is that blending identical faces achieves generating more unrecognizable fake samples than blending different faces, which is proposed in previous methods. Here, we detail the generation pipeline of our self-rendered images. First, source target augmentation is applied to a base image. We adopt 5 image augmentations which are classified into color transformations and frequency ones, as shown in the figure. After the augmentation, the source image is resized and translated to reproduce landmark misalignment and visual blending boundary. The base image is also input into facial landmark detector. Based on the detected landmarks, we take convex hull to generate a mask image and apply some augmentations, including erosion, duration, and smoothing. Finally, we generate a self-blended image by blending the source and target images with the mask image. Here, we show representative examples of SBIs. Each SBI is generated from a single real facial image. We can train deepfake detectors with SBIs under the traditional binary cross-entropy laws. We leveraged standard cross-dataset evaluation protocol to evaluate model generality to unseen domain. In the protocol, models are trained on Face Forensics++ dataset and evaluated on other deepfake datasets. We used 5 datasets that have different manipulations, scenes, or compression rates. Our method achieves state-of-the-art cross-dataset results on 4 out of 5 datasets. Our method is also generalized to training datasets and classifiers as shown in the tables. It can be observed that it is easier to detect deepfakes on known scenes than on unknown ones, even if models do not know about manipulations. Here is some examples of saliency map visualizations. A model trained on FF++ captures method-specific defects which are widely present across forged faces, while a model trained on SBIs focuses on common defects like the blending boundary. Finally, we can come to the following 3 conclusions. Please check our paper for more details. Thank you for your attention.